Hello, and welcome back to Mammalian Anatomy at Keuka College. Today what we're going to do is continue our lesson on Chapter 12, the nervous system, and we're starting Part 4, neuronal integration. In this part on neuronal integration, we're going to learn that neurons do not work in isolation. They synapse together in complex ways, and because of this integration and synapsing, the nervous system is able to create complex responses to our internal and external environment. And not only can we respond to these complex environments just reactively, we can use past experiences and our memories to modulate our responses. So in Part 4, we'll actually have two videos, the reflex arcs and neural circuitry or neural circuits. Part 1, we're going to mainly focus on the reflex arc because it allows us to have a simple illustration of how the nervous system and neurons are integrated together. So it'll allow us to establish our foundation for neural circuitry. Part 2, or the second video of this series, is going to be on neural integration. We're going to look at the different ways neurons can integrate with each other to create these complex circuits. And we're going to look at two different types of processing that the nervous system can use. We'll be able to use this information in the future when we get to chapters 13 and 14. And we look at complex tracks and circuits that are going up and down the spinal cord later on. So save this information for future chapters. So let's get into it. Let's get into the reflex arc. So what is a reflex arc? So a reflex arc is going to be a simple chain of neurons. It usually consists of a sensory neuron, an interneuron, and motor neuron that are connected in a single file. So it's a very simple neural circuit. And this reflex can actually elicit this reflex arc can actually elicit a reflex. So what is a reflex? A reflex is a rapid autonomic motor response to a specific stimulus. So the stimulus is always going to be specific. And the response will be patterned and will always be the same response to the same stimulus. So if you touch a hot stove, your response is always going to be to pull your hand away. So you're not going to touch a hot stove and then shake your hand on the hot stove. That's not the typical response. You're just going to touch the hot stove and move your hand away, and that's going to be the same pattern each and every single time. So there's a link between the stimulus and the response. It's also autonomic. So this is an uncontrolled response. Usually we move our hand away before we even realize what's going on. Reflexes are not learned, so we are born with them at birth, and they're not premeditated. We don't think about, oh, if I touch a hot stove, what am I supposed to do? No, it's something that we're born with, and it's naturally going to occur. Even children, if they touch a hot stove, they'll move their hand away automatically, even if they haven't experienced that sensation before. So that's kind of introducing the definition of a reflex arc and a reflex. But why are we talking about this? It's going to help us illustrate the basic structure of the nervous system and show us how neurons integrate information from the external and internal environment to create a complex response. So let's look at the components of the reflex arc. There's going to be 5 components: a receptor, a sensory neuron, an integration center, motor neuron, and effector. So let's go through it piece by piece. A receptor is going to be a special structure that has the capability of taking a stimulus and converting it into an electrical impulse that the nervous system can understand. So we may not be able to detect things such as light directly using our nervous system, but receptors in our retina of our eyes are going to be able to convert that signal from light into an electrical signal. Similarly, my microphone right now is taking sound waves and converting that information into an electrical current that my computer can understand. So that's really what the job of a receptor is that conversion of information. Here in this diagram, the stimulus is going to be a pin. So there's some sort of pain that's going to be experienced by the skin. And the skin has nociceptors that will detect that pain and convert that pain into an electrical signal. The next part of the reflex arc is going to be the sensory neuron. The sensory neuron will take that electrical signal from the skin and carry it all the way to the central nervous system. In this situation, we're going to be using the spinal cord within this example. Within the spinal cord, we're going to have the integration center. Here, the neurons are going to be synapsing and processing information. And in this situation, we're using an interneuron to connect the sensory neuron and the motor neuron. This way, the sensory neuron can bring the information from the environment, and then the interneuron can tell the motor neuron how to respond. Note that interneurons are not always present in a reflex arc. We'll talk about that more when we talk about monosynaptic versus polysynaptic reflexes. Over here, now, we have a motor neuron. A motor neuron is going to take information from the integration center, and it's going to carry that information to the effector organ and stimulate the effector organ to change its behavior. Part 5 is the effector organ. What is an effector organ? So an effector organ is an organ that actually will change its behavior to create a response in the environment to the stimulus that the body has experienced. Effector organs would include muscles, but it also will include glands such as the adrenal gland or salivary glands, and adipose tissue. So fat can actually respond to reflex arcs as well. So those are going to be the 5 components of the reflex arcs. I would like you to be able to understand each component, how they're connected together, and what is the function of each component within this arc. Now let's look at the different types of classification of reflex arcs. So reflexes can be either somatic or visceral. Remember, somatic has to do with anything outside the ventral cavity, while visceral has to do with anything inside the ventral cavity. So somatic reflexes will help us respond to our outside world for the most part, and visceral reflexes will allow us to respond to our internal environment instead. Let's talk more about somatic reflexes. Somatic reflexes are going to stimulate skeletal muscles as their effector organ. And so things such as the stretch reflex or like the withdrawal reflex would be a good example of a somatic reflex. The stretch reflex is what you experience if you go to the doctor, and if the doctor hits a hammer to your knee and your knee will bounce. Really what's happening is there's going to be muscles being stretched in your quadricep, and the muscles will respond to relieve that stretch. So that would be one example. The withdrawal reflex that we've talked about with touching a hot stove and moving our hand away is also going to be an example of a somatic reflex because we're stimulating the skeletal muscles. In visceral reflexes, on the other hand, we're not going to be stimulating skeletal muscles. Rather, we're going to be stimulating cardiac muscles, smooth muscles, and glands. Also, we can stimulate adipose tissue. This will be responsible for many physiological responses. So, for example, if an individual gets up, controlling blood pressure would be actually a visceral reflex. If a person gets up too quickly, they may feel lightheaded, and that lightheadedness is a signal of having low blood pressure. In our body, specifically in our carotid artery, we have baroreceptors that are capable of detecting changes in blood pressure. Those baroreceptors will be able to convert that sensation of low blood pressure to an electrical signal that can be sent through the sensory neurons to the integration center. So the receptor will detect that drop in blood pressure. The sensory neuron will carry that action potential or that signal to the control center. In this case, the control center is going to be in the medulla oblongata of the brain. And the brain is going to figure out what's going on, and it will determine and integrate that information and be able to understand that there is a drop in blood pressure. As a response, what will happen in that visceral reflex is the brain will send out motor neurons to the heart, and it will also send motor neurons to the blood vessels. It will tell the heart to beat faster, and it will also cause our blood vessels to constrict. Both of these actions are responsible for increasing blood pressure. So you can see the same components of a reflex arc can be used in visceral reflexes as well. You have the stimulus, you have the receptor, sensory neuron, integration center, motor neuron, effector. So all of these things are going to be in both somatic and visceral reflexes. Sorry for the tangent, but I think that one is really cool. I love that reflex. All right. Reflexes can also be monosynaptic and polysynaptic. Remember in our diagram of a reflex, I said that the interneuron can sometimes be optional. And so this is where we're going to talk about that in more detail. Monosynaptic reflexes are very simple. And essentially what's going to happen here is that a sensory neuron will directly connect to a motor neuron. And in this situation, there is no interneuron present. So I'm going to show you the stretch reflex to illustrate a monosynaptic reflex. I want you to know that this diagram is a little bit simplified. Later on, when we get to neural integration, I'm going to show you a more complex diagram of the stretch reflex. So know that this one is more simplified. So let's look at a monosynaptic reflex. I first want to direct your attention over here to the spinal cord, and I want you to notice that the sensory neuron will synapse directly with the motor neuron, and it will lack the interneuron completely. So they'll just communicate directly with each other. So what's happening in the stretch reflex? The stretch reflex is what you experience when you go to the doctor and they hit your knee with a hammer. What's happening in this situation is the hammer is actually hitting the patellar ligament, and it's causing the quadricep muscles to actually stretch. There's a stretch receptor located within the muscles, and the stretch receptor will become activated during this stimulus. It will convert that signal into an action potential, and the sensory neuron will carry that information to the spinal cord, where the sensory neuron will synapse with the motor neuron. The motor neuron will then carry that information back to the quadricep muscles, and the quadricep muscles are going to act as its own effector organ. This motor neuron will stimulate the quadricep muscles to contract, and that will be what's creating that bounce that you experience when your knee gets hit by a hammer. So that would be the stretch reflex. We also have polysynaptic reflexes. Polysynaptic reflexes are much more common, and they're going to be a more intricate and can provide a more complex response to the stimulus. In this situation, the sensory neuron and motor neuron have an interneuron that lie between them, and as a result, it's going to have at least two stimuli. Sometimes you can have even more interneurons that are separating the sensory and motor neuron. Oops. And a good example of this would be the withdrawal reflex. Again, this is going to be a more simplified diagram of the withdrawal reflex, but it illustrates this concept of polysynaptic reflex quite well. So again, I would like to draw your attention first to the spinal cord located over here. And what you can see here in this polysynaptic reflex is that you have a sensory neuron, an interneuron, and a motor neuron. And so one, the interneuron is present here. That is one significant difference. And secondly, you have more than one synapse. Here you have two synapses here. So that's where polysynaptic reflex gets its name. It has many synapses. This is showing an example of the withdrawal reflex. In this situation, we're going to have a pin, and the person will accidentally touch the pin, and the sensory receptor will convert that pain into an electrical signal that the nervous system can understand. What will then happen is that the sensory neuron will carry that information to the spinal cord, and the sensory neuron will synapse with the interneuron. The interneuron will help process and integrate that information, and will then connect to the motor neuron and tell the motor neuron how to respond. The motor neuron will become activated here in this situation, and the motor neuron will carry that information down its length and eventually stimulate the effector organ to respond. In this situation, the biceps brachii, the brachialis, will contract and pull the hand away from the stimulus. So thank you for listening to our conversation about our reflex arcs. I hope you can have a good foundation to see how sensory neurons, motor neurons, and interneurons are going to start to synapse together to create complex responses to that stimulus. And it will teach you kind of the foundations of how neurons will actually integrate together. And we'll talk more about it in the next video, and then go into much more detail when we get into chapters 13 and 14. Thank you very much and have a good day. Be good to yourselves. Bye-bye.